Hello everyone, and today in this lecture I will be talking about Lorentz transformations, and this part of the series is made for the students who have already done a course on special relativity, who has some basic knowledge about it, and it will be using Einstein conventions and tensor analysis and things like that. So I am assuming that the viewers, they have previous knowledge about those topics. So yeah, let's start. Okay, so what is Lorentz transformations? Principle of special theory of relativity states that the laws of nature, that means the physics, the laws of nature are invariant under a particular group of transformation, and they are the space-time coordinate transformations, and that group of transformation is called the Lorentz transformation. And before Lorentz transformation there was Galilean transformation, and the Newton's laws were invariant under Galilean transformation. So for a long time it was thought that Galilean transformations are the required transformation group for space-time coordinate change. But then Maxwell came up with his four famous laws of electromagnetism, and then we saw that the Maxwell's laws are not invariant under Galilean transformation. So there was a problem, and that problem was resolved by Einstein when he stated that instead of Galilean transformation we need to use Lorentz transformations, and Maxwell's laws are invariant under Lorentz transformation. So for two different observers, the laws of electromagnetism are always the same. And previously, mathematically, for two different observers, the laws of electromagnetism may not have been same under Galilean transformation. So yeah, so I'm going to write the definition of Lorentz transformation. Suppose we have a space-time coordinate x alpha, a vector, coordinate vector, this is a 4 vector, and we want to transform it to x prime alpha, and that will be related to x alpha by this expression, lambda alpha beta x beta plus some a alpha. And here a alpha and lambda alpha beta are constants, pardon me. Okay. And there is also a further restriction about lambda alpha beta, and that is lambda alpha gamma, lambda beta sigma, eta alpha beta will be equal to eta gamma sigma. And eta is here the metric of Minkowski space-time, and this is generally written like this. It's a matrix with diagonal elements 1 or minus 1. Well, there is another way to define the metric in Minkowski space-time, and that is by setting this one positive one and the remaining three negative ones, but it's totally upon the convention that we want to use. In this lecture and on the next lectures, I will be using this particular metric, this convention. Okay. So now we are going to delve deep into this matter, and some basic concepts, some basic pre-arrangements that I am going to write, and we will be working in natural units. In natural units, the speed of light in vacuum, that is c, is 1. It's taken to be 1, and so when I am writing a velocity, the value of the velocity is always less than 1, because nothing can go faster than speed of light. And one small recap, x alpha, this is the 4 vector, and the Cartesian components of this 4 vector I can write like this. This is nothing but the x0 component is nothing but the time, and the remaining 3 are nothing but the components of a position vector in 3D. So I'm going to write x vector, these 3. The usual vector that we learned in high school, the position vector. Yeah. And now, and remember we are using here Einstein summation conventions. Now, Lorentz transformations are like rotations. Rotations in 3D space. I hope you have learned that. In case of rotation, if we rotate the coordinate system, then they keep the magnitude of the position vector invariant. Like there is an origin and there is some point. Suppose it's in r distance between them. There is r distance between them, and if I rotate the coordinate system, or if I rotate the point in some circular manner, the distance between the point and the origin will remain invariant, and it will still be r. And yeah, so in case of Lorentz transformations, there is also a thing, a quantity that remains invariant, just like the magnitude of position vectors in case of rotations. We have the proper time in case of Lorentz transformation. I'm going to define what proper time is. So Lorentz transformation, they leave the proper time invariant. Okay. Invariant, what is invariant? The proper time. We generally write it with tau, the d tau, the change in proper time. And this thing is defined like this. D tau square is nothing but dt square minus this. And dx vector square is nothing but the dot product between two dx vectors. Dx vector dot dx vector, that I am writing as dx vector squared. And as I have previously written, the convention of my Minkowski metric and the Cartesian components of the position vector in 4D space time in our case, we can write this in a tensor form, or using Einstein summation, we can write this like this. This is exactly the same. If you know Einstein summation convention, then you just sum it and you will get this thing. Now, I am claiming that this d tau, it is invariant under any Lorentz transformation. So I need to prove it. Okay. So before proving how d tau changes under Lorentz transformation, we need to see how dx changes under Lorentz transformation. So we previously have written that this is the typical Lorentz transformation. So the change in between any 2 points in space time, let that be dx alpha, that will be looking like this. This is just a constant quantity getting added with all the points in this new coordinate system this is called the translations. So if we are taking differentials of the coordinate systems, then we do not need to worry about it because it gets cancelled out when we are finding the difference between 2 points, the distance between 2 points. Okay. Now we will see that if in our new coordinate system, the prime coordinate system, let's say our proper time is d tau prime, and squaring it, we will use the same equation. It will look like this, right? Just writing the prime coordinate systems, writing the primes everywhere. Not here because the metric is a constant, it's always -1, 1, 1, 1, the diagonal elements. And now we will replace these prime differentials using this equation, and what we will have is this. Okay, so here I'm going to write lambda alpha some rho times dx rho, and for this one I'm going to write lambda beta sigma with some dx sigma. And I previously wrote on the board that the lambdas, they are restricted by a particular property, that this thing is equal to the metric itself, and I had written it before in the first part of the video. You can rewatch it, and using that you can see that this thing is exactly equal to eta rho sigma, and there is a minus sign behind it, and these two quantities. So this is exactly this thing. Using Einstein's summation convention, the dummy indices, we can write dummy indices using whatever symbols we like. We need to take care that we do not write the same indices more than twice. Okay, so this is exactly equal to d tau squared. So mathematically we have shown now that this proper time is the invariant quantity under Lorentz transformation. It doesn't get changed. Beautiful. Okay. And fun thing is, this exact property, that the proper time is invariant, is the reason that the speed of light is same in all inertial frames. I will show you that. Okay, so now I am claiming that the speed of light in vacuum, which is c, in our case in natural units we took it to be 1, and that will be same for all reference frames. Okay, let's see. I'm going to erase that. I'm going to erase the heading also. Okay. For a light wavefront, a light wave, the velocity looks like this, right? And the magnitude of this is nothing but c. In our case, it is 1. Okay. So, for light, the proper time is, for light, the proper time is dt squared minus dx squared, right? We previously wrote this. This is the definition of proper time. And if we take dt squared common, what we will have is this. And we can write whole square or mod square, it's the same. And this thing is exactly 1, so 1 minus 1 will be equal to 0. So for light, the proper time, the difference of proper time is 0. Okay, so now if we change using some Lorentz transformation, and we have the proper time of light for some other observer, we previously have shown that this thing will be exactly equal to this thing because the proper time doesn't change under Lorentz transformation. So this thing will also be equal to this, the previous one, and we found it to be 0, so this thing is also is 0, and this thing is nothing but some dt prime squared minus dx prime squared. This will be 0, and taking dt prime squared common, we will once again have the similar equation. This will be 0, and as the time differential, or the difference between time in 2 points, it's arbitrary, and we have not specified 2 points, so we cannot say that this is 0. We must have this one 0 for all time. So this one can only be 0 when this is exactly equal to 1, and this will be exactly equal to 1 when this thing is equal to 1 or minus 1, depending upon the direction of the light beam, but the mod will be 1. So for our first reference frame, light speed was 1. We saw that the proper time for light doesn't change and it's always 0. And then we Lorentz transformed it, and we saw that the proper time is same also because it's invariant. And now what we get here is the speed of light in our new coordinate system, or the speed of light for our new observer, is also equal to 1, that is the same here. So that is the proof that the speed of light doesn't change for two different observers. Galilean transformation didn't allow that, and because of that only the Maxwell's equations were not invariant under it. Okay. Now we will see that Lorentz transformations are the only non-singular coordinate transformations that can leave the proper time invariant. What do I mean by non-singular? Non-singular means these two functions, the function of the unchanged coordinate with respect to the changed coordinate and the changed coordinate with respect to the unchanged coordinate or the non-prime coordinate, they are well behaved such that this quantity, this matrix, this is a matrix with index with indices alpha and beta, this is a square matrix, and this will have a well-defined inverse, that is this thing. That is the meaning of non-singular. So if this exists, then this will also exist for non-singular transformations. Okay, so I am claiming now that to keep the proper time unchanged or invariant, Lorentz transformations are the only options, are the only non-singular options, and I will show you that right now. So let's start. I'm going to erase this. Let's write any general transformation. That's any general transformation. Let that be x becoming x prime, and this will change the proper time like this. D tau will become d tau prime. We will later require that these two are same or invariant under this coordinate transformation, and we will see that these two will be, if they are non-singular, they will be exactly related by the first Lorentz transformation equation that I wrote on the board. Okay, so how will it change? The proper time looks like this, right? Okay, and using partial derivatives, I can write this like this. Okay, but I'm going to write a different index here. I have different index in my note. I'm writing them the same because otherwise I can make some silly mistakes. Okay, I am requiring that this will be equal to this thing, or let me say what's this. Okay, I'm requiring this to be equal to the proper time in our non-changed coordinate system or the non-prime coordinate system. And comparing these two, we will have a beautiful equation that this needs to be true if we want the proper time to remain invariant. And we will now exploit this equation to find out some more information about the transformation. Okay, so what I'm going to do now, I'm going to differentiate this equation with respect to some differentiate with respect to some x epsilon. Okay, and one thing you should remember that eta is a constant, or eta alpha beta is a constant. It's just a number because the eta matrix or the metric, it has only constant values, -1 and 1 and zeros. So if we differentiate it with something, we need to treat it like a constant. Okay, so now if we want to differentiate, what we'll have here, we will have eta alpha beta, and now we need to differentiate this. You need using the limits rule or the UV formula, whatever you say, and we will have this thing. This will be equal to 0 because this is a constant. Okay. Now what? Now we will be doing a very lengthy calculations. So get prepared with a cup of coffee. We are going to write the same equation thrice. With the second time we write, we will be substituting gamma and epsilon and adding with the previous equation, and on the third one we will be substituting epsilon and delta, and then we will be subtracting, and all three are equal to 0. So the addition and subtraction, all the total thing will also be equal to 0. So if I write this again and add it, by replacing gamma and epsilon, what I will have is this. And now I am going to replace the delta and epsilon and subtract with it. So what we will have is something like this. Delta and epsilon, yeah. This whole thing will be equal to 0. Now, see that this term, the sixth term, is exactly equal to the second term, as the partial derivatives, they can commute among themselves. So they will cancel each other out. And the fourth term here and the fifth term here, they are also same because they are summed with eta alpha beta, and it's a symmetric matrix. So eta alpha beta times this thing minus eta alpha beta times this thing. So on the second term, if we replace alpha and beta, interchange them, and then it will be eta beta alpha, and that will be equal to eta alpha beta because the metric is symmetric, and then they both will be same and will get cancelled out. Now we are left with these two things, and they are also exactly the same, so they will get added up, and what we will have here is this. This equal to 0. Wonderful. Now, eta alpha beta is non-singular, right? Because the determinant of this is not 0. And also this thing, we previously stated that we want a non-singular coordinate transformation that says that this thing is non-singular. That means the determinant of this matrix is not 0, and this has a well-defined inverse. So this quantity can, and also 2 is not 0. So this whole quantity can only be equal to 0 for a non-singular coordinate transformation when this term is equal to 0. So what we have from here is this thing, right? Yeah. Okay. Now just I'm going to write this here once again. I'm interchanging epsilon and gamma here because the partial differentiation commutes. So this is. Now, this is exactly this thing. Okay. So this means that differentiating this term is always 0. So that means this term must be a constant. So we need to name our constant something. I'm going to name it lambda, and to match the free indices we have to write alpha here and gamma here. It's just a matrix with constant components, and see that the solution to this equation will look like this. This will be equal to plus some constant. And if you differentiate this with respect to gamma, x gamma, then you will have this exact equation. So what we are getting here is the same equation that I wrote with the very first in the very first part of the lecture. And yeah, so indeed we are getting a unique type of non-singular transformation. If we want to keep the proper time invariant, d tau prime will be equal to d tau, then this must hold. So Lorentz transformations are the only non-singular coordinate transformation that keeps the proper time invariant all the time. Okay. Now there is a fun thing about it. In this case, the proper time is invariant always under Lorentz transformation. If we wanted the proper time to remain same only for light and not for other massive particles, then we would have got some non-linear transformations. This is linear, but if we wanted the proper time to remain unchanged only for light and not for other things, then we would have got some non-linear coordinate transformations. And in Lorentz transformations, in this particular case, we have this group is a 10 parameter group. I will be discussing about that in a moment. And the non-linear group that we could have got if we used if we didn't demand the proper time to be invariant for massive particles, then we could have got a 15 parameter transformation group, and that is called the conformal group. But the thing is, if conformal transformations were a symmetry of this universe, the first Newton's law will not have been same for all observers. That means for me, if I am stating that the Newton's first law is true for a different observer who is related to me by conformal transformations, whose coordinates are related to me by conformal transformations, he or she may not agree with me. In his reference frame, Newton's first law can be invalid. He can see that a free particle with a fixed velocity can change its velocity, which is not true in our world. So that's why we will not be dealing with conformal transformations in special theory of relativity. Okay. So Lorentz transformations, they look like this. And here there are four translations, four parameter group of translation. This I'm sorry, this is not a group. The only translations doesn't make a group. I think here we will need all of them for this particular operation. Okay. Yeah. So there are four parameters here, translations along the four directions in 4D space time, and this has total of 6 parameters, 3 rotations in xy plane, yz plane and xz plane, and 3 boosts in x direction or in xt, or boosts are nothing but rotations in a time and a space plane. Suppose a rotation in xt plane, that will be a non-Euclidean kind of rotation, and we need to use hyperbolic trigonometric functions to form the rotation matrix, and that will be exactly equal to getting a particle to some velocity along that direction x. So that's what we call boost. So there are a total of 4 plus 3 plus 3, 10 parameters. A 10 parameter group. And this is called the inhomogeneous Lorentz group or the Poincare group. If we set A alpha equals 0, that means if we exclude the translations, we will get a subset of the Poincare group that will contain only 3 rotations and 3 types of boosts. So that will be a 6 parameter group, and we will call it the homogeneous Lorentz group. This is inhomogeneous, this is homogeneous. Okay. And both homogeneous and inhomogeneous Lorentz group can be divided into some parts, and we call them proper if they maintain some properties, and I will be diving into that right now. Okay. So now we had this equation . I am maintaining the index notations according to the note I have made, so that I don't make any mistakes. And now if I set sigma and rho both equal to 0, then I will get something like this. Sorry, eta alpha beta lambda alpha 0 lambda beta 0 equal to eta 0 0, that is minus 1. And this thing is exactly equal to lambda 0 0 squared, sorry, minus lambda 0 0 squared plus summation of lambda I 0 squared. Yeah, and I goes from 1 to 3, so I has 3 values, 1, 2 and 3. I am writing ij, I will write ijk for space indices that will go from 1, 2 and 3, and using the Greek indices alpha, beta, gamma, rho, delta, they will be going from 0 to 4, sorry, 0 to 3, 0, 1, 2, 3, they will have 4 terms there. Okay, and I can write this like this. Now this is a square term, and as these quantities are real, so this whole thing should be greater than or equal to 1, because this is positive and adding 1 with some positive thing will be obviously greater than or equal to 1. And another thing that we can get, if we take determinant of this equation, if we take determinant, we will get determinant of eta is nothing but -1. So -1 times determinant of lambda times determinant of lambda, so that gives determinant of lambda whole squared equal to -1. So this will give us determinant of lambda square equal to 1. I'm going to write this here also. Determinant of lambda square is 1. Okay. Now, see, lambda 0 squared, this is always greater than or equal to 1. So lambda 0 can be greater than or equal to 1 or can be less than or equal to -1. Both will satisfy this thing. And determinant of lambda whole squared is 1. That means that determinant of lambda can be 1 or -1. So we will have 4 types of Lorentz transformations, or not types, I don't know what to say, I'm just writing them down. Lambda 0 greater than 1 and determinant of lambda equal to 1, this is type 1. I can have lambda 0 less than or equal to -1, determinant of lambda is +1. I can have lambda 0 greater than 1, but determinant of lambda is -1, or I can have both of them negative. Okay. Now, a fun thing is, any Lorentz transformation that we see in nature that can be expressed, or that can be converted to a sum of infinitesimal transformations. That means what we see in nature are continuous transformation and they form a group. Okay. But if we include all the 4 parts in our Lorentz group, the transformation group, then we will not have a continuous group, because going from this section to this section will require us to do some time reversal, and going from this to this will require us to do some space inversion or parity, space inversion, and going from this to this will require us to invert both time and space, time reversal and space inversion. But these transformations are not at all continuous, they are discrete. And what we see in nature is continuous. And also, time reversal highly suspectfully, it's not an exact symmetry of nature, and also we know that space inversion is not an exact symmetry of the universe. So we will only be dealing with this part. We will exclude all those 3 because from it will require us to use space and time reversals to jump between these parts. So that's why we will use only this part, and we will say that any Lorentz transformation in our nature that connects the coordinate systems between two different observers, that will be maintaining these two properties. The determinant of that lambda will be 1, and the 0, 0 component of lambda will be greater than or equal to 1. So that's why we will be using only this part. That's why it's also called the proper orthochronous group. Proper means the determinant should be 1, and orthochronous means that we have set the direction of time in a particular direction. We are not reversing times inside the group. Okay, so we have set the time here from past to future, and we have set the group to be proper. That's why it's called a proper orthochronous group. Okay, so we are not dealing with these three parts, so I'm going to erase these three parts. We will only have this one part here, and I'm happy because I'm not dealing with any discrete transformations. They can be nasty sometimes. Okay. Now, this thing has another subgroup, a further subgroup, and that is nothing but the spatial rotations that we have learned in classical mechanics classes. And in case of spatial rotations, lambda ij is nothing but this thing, rij. I hope you know that because I am expecting you to know about rotations. Rij is nothing but the rotation matrix, and that relates the coordinate systems between an unrotated and a rotated reference frame. And lambda I0 and lambda 0I, they both are 0, and lambda 0, 0 is 1. So this thing, if we further restrict this to be this, then this group will be our rotation group. And Rij is unimodular and orthogonal. That means the determinant of R is 1 and they are orthogonal. And remember, I and j runs from 1, 2 and 3, not from 0. So this is the rotation subgroup. Of this proper orthochronous group. Transformations consisting with these rotations and simple 3D translations, they together make the Galilean transformation group. The difference arises when we include the boosts. Previously, the Galilean transformation, it had these two things, and everything was smooth until Maxwell arrived, and we needed to include some boosts. Okay, so we will see how that is relevant, and we will see that how in generally we can write any component of this lambda, including the boosts, rotations and the translations. Okay. Suppose I have two observers. One is O and one is O prime. O is seeing a particle to be at rest, but O prime sees the particle to be moving with some velocity v. What they see, what O and O prime see. Okay, O sees the particle to be at rest, and O prime sees it moving with velocity v vector. And we previously wrote that the differential of Lorentz transformation looks like this. The prime coordinates are nothing but the coordinate system of O prime observer, and the non-prime are the coordinate systems of the observer O. Okay. So dx prime I, that means the spatial part, this will be lambda I beta dx beta. Okay. Now, one thing you need to remember, and you need to be careful about that, as O is saying the particle to be at rest, O is saying that that dx vector is 0 because the particle is not changing position, it's at rest. Only the dx 0 part, or the time of that particle is changing, is evolving. Okay, so dx vector is 0 here. So using that, if I expand this using an Einstein convention, we will have lambda I 0 dx 0, and the next part, lambda I j times dx j, it will be 0 because dx vector is 0, and dx 0 is nothing but the time evolved in O reference frame. So I can write this using our known symbol t for time, and also this is exactly equal to the change in position seen by the O prime. Now the change in time seen by the O prime, or dt prime, this will be equal to lambda 0 beta dx beta. Using the same condition, we will have lambda 0 0 dx 0, that is lambda 0 0 dt. Okay. So we have two equations. One, dx prime I is lambda I 0 dt, and dt prime is lambda 0 0 dt. So now we will find dx prime I divided by dt prime, and that's nothing but the velocity seen by O prime, that's vi, the velocity, and this will be equal to dx prime I is this thing, lambda I 0 dt, and dt prime is this thing, lambda 0 0 dt. So this is nothing but lambda I 0 divided by lambda 0 0. Oh, this pen's losing ink always. Just a minute. So what we have here is, using this equation, lambda I 0 is exactly equal to vi times lambda 0 0. And we also previously wrote that lambda 0 0 squared is nothing but this thing. We got it from the restriction of lambda, that's eta alpha beta lambda alpha rho times lambda beta sigma is equal to eta rho sigma. So from there, by setting rho and sigma equal to 0, we got this equation in just a few minutes ago. So I'm going to substitute lambda I 0 from this equation to here, and I will have is this thing, and this will be vi lambda 0 0 squared, and I can take lambda 0 0 out here, so it's lambda 0 0 squared times summation of I vi squared, and this thing is nothing but the v vector squared, or the dot product of two v vectors. So I can write this safely as v vector squared. So v vector dot v vector, or v squared, whatever, anything. I want to use less ink, so I'm not writing the arrow. So using this, if we solve, we will get the lambda 0 0. We will take lambda 0 0 squared times v squared to the left hand side, and then we will take lambda 0 0 squared common and put the rest to the right hand side, and then take square root, and we will have lambda 0 0 to be 1 over 1 minus v squared. V squared means V vector dot V vector. And we call this, we name this gamma, the famous gamma. So we got here that lambda 0, 0 is nothing but gamma. So if that is true, then lambda I 0 is Vi times lambda 0, 0, so it's Vi times gamma. Okay, yeah. And now for the other components of this famous lambda matrix, and we need to acknowledge something, that the other components are not uniquely determined. In generally, if I want to write lambda alpha beta, I cannot say that there is a unique solution to that. So we only need to satisfy this equation, and this thing needs to be true, and the other components, they may not be, they are not unique, so we need to find some convenient choice, and that choice is nothing but lambda ij equals delta ij plus vi vj times gamma minus 1 divided by v squared. Okay, so we have gammas, we have lambda 0, 0, okay, we have lambda 0i, that is this thing, and from this we can find lambda lambda I 0, from this we can find lambda 0i, and yeah, lambda 0i will nothing be, we will have the index in the lower position. So yeah, and we have in general lambda ij equal to this. So we have all the components. There is one here, and here I think there are something 1 2 3 1 2 3 6 here. Okay, 6 plus 1 7, together they have 6, and here I think 9 components. Yeah, so 7 plus 9 is 16, the total components of a 4 cross 4 matrix lambda alpha beta. Okay. So lambda alpha beta is nothing but lambda 0, 0, lambda I 0, lambda 0i, and lambda ij. Okay. So now we have a decent understanding of Lorentz transformation, and I am going to conclude this here at this stage, and we will see some interesting topics in some next video. Thank you.